Hi again and welcome. This is part 2 of horizontally launched projectile. I want to just finish up the problem previously where I was going to look at the landing velocity of this object. So going from the previous scenario here, like this. Actually, let me do this for now. There we go, a nice clean picture, right? Perfect. I want to calculate this V right here. So if I draw the ground up here for a moment, we know that the object's going to land at an angle. So it's terrible, so go with that, like that. So when it asks for a landing velocity, it wants this velocity. So the idea to find this is we got to find the components that make up this triangle. So we need to find a Vx. A Vy, I'm sorry, Vy, my apologies. Clearly this is Vy because it's vertical, and this is Vx. So if I find Vx and Vy, I can solve this triangle for V right here, and I could get even more information is the angle at which it strikes the ground according to the horizontal. So if you notice here, this is alternate interior angle, so I can solve that there. So here's how we're going to do it. So we know that this velocity, this is from the problem, was 223 meters per second. So I got that from the context of the problem. The good news is that Vx is always constant. So with no calculation, woohoo, we can write that in. Yay. So that's not too bad. What we need here is the y. Vy final. Because remember, Vy initial is 0 up here. So it's not too challenging. And we know how far it went to get there, the 900. So using this information, I have VIY, y final is what I'm trying to find. I have delta y, and acceleration. So again, these problems look so empty. They only give us a few numbers. But remember, these are implied, these two right here. So I can find the final velocity by using this kinematic equation. And I can find the final. The good news is this goes to 0 because that's just 0. That's the initial. So Vy final simplifies as 2a delta y 2a. Sorry, I'm squeezing the information here. That says 2, 9.81, and 900. And then, of course, I got to square root that to get the final velocity. Oops. Sorry, square root the answer. So I get a pretty large velocity. I get 132.88. But we noticed that our x was pretty comparable. It was pretty fast like that. So what I did is find the y component of the velocity at the bottom. I have the x component, which is the horizontal because it doesn't change. So essentially it becomes a triangle where this is the 132.88. You notice I threw in the negative sign to represent the down. And then our x is should be, I'll draw it to scale, so it's doing something like this, right? It's pretty large, is 223 meters per second, like that. And I'll just put the dotted line because that's what we're solving for. So as you can see, we have one piece of the triangle and the other. We can use the Pythagorean theorem. So a squared plus b squared equals c squared. So I'm going to write this out as v in this form is going to be vx squared plus vy squared square rooted, right? That's because I'm saying vx squared plus vy squared equals v squared. The Pythagorean theorem, and I just wrote it out like this. So I could write it out in one step, and it will be that. So Vx is the 223 meters per second squared plus the Vy. Now you could put the negative in here, but I'm taking a shortcut because I know it's just going to get rid of the negative go away because of the squared. So I just usually don't write it in for that reason. But I do acknowledge, and I will say it, that it is technically negative because it is moving downward. So I'm calculating the value now, and I get V should be somewhere larger than that, and I do. I get 259.59 meters per second. So I just calculated the hypotenuse right here, 259.59. Now that's the speed at which it hits, but it's good to know this angle right here. How, what was the angle below? So notice that if I want to find this angle, I basically can find this angle using alternate interior angles. So I'm going to solve for this angle right here. You can use any part of SOHCAHTOA to solve this. But since usually I have x and y, I like to use tangent, because tangent is opposite over adjacent, and this is hypotenuse. So opposite over adjacent is tangent of the angle. So I could solve for angle here. So the tan of the angle. So I had to take the inverse to get the angle itself. So that's going to be opposite, which is 132.88 meters per second, divided by the adjacent, which is the 223 meters per second. That's going to solve for angle. So I have to press second tangent, 132.88 divided by 223, like that. And as long as I'm in degree mode, it should come out correct. So double check your calculator. But I get a 30-degree angle. So the final answer of the landing velocity would be 259.59 meters per second at. So I'm going to say this is representing the angle below the horizontal, so 30 degrees, 0.7 below horizontal. Now, the reason why I write it below the horizontal like that is to represent where I'm taking the angle. So notice that I'm taking the angle from here. 30 degrees above would be a whole different type of problem, so that's why it is important that you specify where you do it from. So that would be the landing velocity. So we have to use a little bit of trig in a triangle to solve that out.